Hello and welcome to my lecture series for Control System 1. This lecture series is designed for 5th semester BTech Electrical Engineering students. Myself, Shumon Ghosh, as a course coordinator, assistant professor from Department of Electrical Engineering, Guru Nanak Institute of Technology, Kolkata. This particular PPT is designed for lecture 13, 14th and 15th. And today is our 15th lecture. So these are the contents of lecture 13, 14 and 15. In our previous lectures, that is 13 and 14, we already discussed the topic of characteristics equation, pole locus of a second order system with variable damping ratio, that is zeta, and stability by pole allocation, and Routh-Hurwitz criteria and its application, and some more related workout problems. In this last lecture of this particular PPT, that is lecture number 15, we will discuss on some workout examples using Routh-Hurwitz criteria and relative stability, which I will see with the help of Routh-Hurwitz criteria. So moving to our today's topic, before going to our today's topic, let us a quick recap. So this is our characteristics equation that is represented by 1 plus GSHS is equal to 0, where GS is the forward path transfer function and HS is the feedback path transfer function. And these are the pole locus of the second order system with variable damping ratio. And here in this figure we concluded that if the poles are present in the right half of S plane, that means in this red shaded area, then the system is unstable condition. That is, the red shaded zone is the unstable region, and this green shaded zone, that is, if the poles present in this green shaded area, that is left half of the S plane, then the system will be stable. And if there is any pole in the imaginary axis, in this axis, that is j omega axis, then the system will be marginally stable. So there are three conditions, that is stable system, unstable system and marginally stable system. And if the poles are present in the right half of S plane, then the system is unstable. If the poles are present in the left half of S plane, then the system is stable. And if the poles are present in the imaginary axis, then the system is marginally stable. So these are the Routh-Hurwitz stability criteria, and we have to check the first row of the Routh array, and if all the elements are of same sign, then the system is stable. If there is any sign changes, then the system will be unstable. And if the system is unstable, that means there are some poles present in the right half of S plane. Then the question arises, how many poles are present in the right half of S plane, and that will be calculated how many sign changes are there in the first column. How many sign changes are there in the first column? Suppose there are two sign changes, that means one plus to minus and again minus to plus, that means there are two sign changes, then there will be two poles that will present in the right half of S plane. Okay, so that's the basic thing. And if there any row present which is divided by a common term, then you have to divide it and just write it. This is one rule, and there are one special case, that is if zero coefficient in the first column of the Routh array. If there exists a zero coefficient in the first column of the Routh array, then what we have to do? Then we have to replace that 0 with epsilon, where epsilon tends to 0. Epsilon, the value of epsilon is nearly equal to 0 but not 0. So you have to replace 0 by epsilon and then continue the process. And after that, when you have to calculate the stability of the system, then just put epsilon tends to 0 and then calculate the value of the here epsilon tends to 0 and then calculate the value, which becomes minus infinity in this case, and then you calculate the stability of the system. Now moving to our today's topic, that is if any row of the Routh array become 0, any total row of the Routh array becomes 0, then what we have to do? Then how we can find the stability of the system? Now when the row 0 occurs, this situation occurs when the characteristics equation has a pair of real roots with opposite sign. Complex conjugate roots on the imaginary axis, that is j omega axis, or a pair of complex conjugate roots with opposite real parts, that is minus a plus minus jb or plus a plus minus jb. Okay, just show the pink color. This is one root and this is one root. The two roots are opposite to each other in sign but not in magnitude. One is at positive real axis, one is at negative real axis. Okay, so these two poles are opposite, and this green color says these are opposite. So if this situation arises, then there will be a chance of a row 0 occurs in the Routh array. Now let us take one example, that is check whether the system given by the characteristics equation is stable or not, where the characteristics equation is represented by AS is equal to 1 plus GSHS. We all know that 1 plus GSHS is equal to 0 is the characteristics equation. So the characteristics equation is given as s to the power 5 plus 5 s to the power 4 plus 11 s cube plus 23 s square plus 28 s plus 12 is equal to 0. So if you apply the Routh-Hurwitz criteria, that means your highest power is s to the power 5. So just put the coefficient of s to the power 5, then alternately put the coefficient. That means if you put first the coefficient of s to the power 5, then you have to take the coefficient of s to the power 3, that is sq, then you have to take the coefficient of s to the power 1 like this. So s to the power 5, the coefficient of s to the power 5 is 1, that's why 1 is here, and 11 is the coefficient of s to the power 3, so 11 is here, and 28 is the coefficient of s to the power 1, that's why 28 is written here. And next you have to write s to the power 4, and the coefficient of s to the power 4 in the given problem is 5, that's why 5 is here. Then you have to put the coefficient of s square and s to the power 0. So the coefficient of s square is 23, that's why 23 is here. And next the coefficient of s to the power 0, that is 12, so 12 is here. So you have to apply the Routh-Hurwitz criteria, that is 5 into 11 minus 23 into 1 divided by 5. So just put and calculate, and it will become 6.4. And again you have to calculate like this, and you got 25.6. Next 3 here, next 12 here, and the next step in this next row, if you calculate further, then you find that the two element, all the elements of this row become 0. Now what you have to do to go further? So this row is the row of zeros. So if this situation occurs, if this type situation row 0 is occur, then form the auxiliary equation as is equal to 0 by the use of coefficient from the row just preceding to the row of zeros. That means you have to write a auxiliary equation just above, by using just above the row, just above the 0 row. This is the 0 row, just above the 0 row is this row. By using these coefficients 3 and 12, you have to write a auxiliary equation. Now take the derivative of this auxiliary equation das by ds with respect to 0, and replace the row of zeros with the coefficient of das by ds. And next, as usual, the process next continue the Routh-Hurwitz criteria. Okay, so how you have to do? So here this is the row 0, and just above, just take the above row, that, and the elements of the above row is 3 and 12. So the auxiliary equation become 3s square 3s square plus 12 into s to the power 0. Alternatively, if 3 into s to the power 2 is there, then 12 into s to the power 0 will be there. So the auxiliary equation become 3s square plus 12. This is our auxiliary equation. Okay, so you have to find the derivative of that auxiliary equation, and that become a das by ds, and it becomes 6s. Now put the coefficient of the auxiliary equation, that means 6. Here 6 is the coefficient. Now put the 6 in place of here. Okay, so just put s to the power 1 row, just look, s to the power 1, there is 6, and this is the coefficient of 6s, which I got from the derivative of the auxiliary equation. And then again follow the next step as usual. Okay, so, and after calculating, this will come. So if you want to uh, calculate the stability of the system, if you want to find that stability, then just check the first column, and it is seen that there is no sign change. All the elements of the first column is positive. That's why the system is stable. Okay, so this is a special case when actually there is no sign change, so that's why the system is stable. Okay, and all the roots have negative real parts, and if you calculate the roots, that means poles of the system, using this characteristics equation, then you can find these are the roots of the characteristics equation. And you can see that there are two roots in the complex, in the S plane. There are two roots in the imaginary axis of the S plane, that is plus minus j2. And for these two roots, for these two roots the systems are marginally stable. So you have to keep in mind, if there are any rows which are comes 0, total row comes 0, then the system will be marginally stable. You have to keep in mind. And if there are no sign changes in the first column and all the elements of the first column has same sign, okay, then the system is marginally stable. Okay, so this is one special case. And next, moving to our next example, that is the characteristics equation of a feedback control system, that is s to the power 4 plus 20 s cube plus 15 s square plus 2s plus k is equal to 0, and determine the range of k for the system to be stable. Can the system be marginally stable? If so, find the value of k and the frequency of sustained oscillation. Okay, just put the value in the Routh array like this. We already know how we can calculate that. Then for question number 1, determine the range of k. Just put all the k related term, this is last two term, all the k related term greater than 0, so that all the elements of the first row become greater than 0. That means positive. So if you put that two term greater than 0, then there will be a range, that is k in between 0 to 1.49. So the range of k for the system will be stable, that is k is ranged between 0 to 1.49. Now in question number B, can the system is marginally stable? If so, find the value of k and the frequency of sustained oscillation. Now for marginally stable case, that means the highest value of k, that is k is equal to 1.49, if you put, then this equation becomes 0. Now we already say in our special case that if any row of a system becomes 0, then the system is marginally stable. Okay, so if this total row becomes 0, then you have to take the previous row by using the previous row coefficient. We have to write the auxiliary equation. So just write the auxiliary equation using the previous row, that is as is equal to 14.9 s square plus k is equal to 0, and just derivative it. So from this auxiliary equation we just find that s is equal to plus minus j 0.316. Now s is equal to sigma plus j omega, and from this j omega, omega becomes 0.316 radian per second. So that is our frequency of sustained oscillation. Okay, now the frequency of sustained oscillation means the system is marginally stable case. Now when the marginally stable case occurs, now when there is a row 0. Okay, so that's why you have to take the previous row coefficient as a auxiliary equation and find the frequency of sustained oscillation. That's it. Now, what is relative stability? Now, Routh stability criteria provides the answer of the absolute stability, but in many practical cases it is not sufficient. That's why we require the information about the relative stability. Now, a useful approach for examining relative stability is to shift the S-plane. That means you have to shift S-plane. Just look at the figure. You have to shift S-plane from here to that Z-plane. So you have to substitute S is equal to Z minus sigma, where sigma is a constant. Now just put S is equal to Z minus sigma, then just continue the Routh array and find the stability of the system. Just look at one example. Check whether all the roots of the equation, that is s cube plus 7s square plus 25s plus 39 is equal to 0, have real parts more negative than minus 1. That means you have to find, is there any poles? Is there any poles in the real part, real negative part more than minus 1? So how we can find this? Just put S is equal to Z minus sigma. So in place of S, just put Z minus 1. Here minus sigma is equal to minus 1. Okay, so put, so in place of S, just put Z minus 1. So S cube becomes Z minus 1 cube plus 7 Z minus 1 square plus 25 Z minus 1 plus 39 is equal to 0. So after applying the formula a minus b whole cube and after simplifying, you just get the result like this: Z cube plus 4Z square plus 14Z plus 20 is equal to 0. Now put the Routh array criteria here. Just calculate the Routh array like this, Z cube like this, and after calculating or after investigating, we can see that the first column of the Routh array, there is no negative no sign change. There is no sign change. Okay, so that's why the system is stable. But since no sign change in the first column, the roots of the characteristics equation lie on the left of the z-plane. That means all the roots of the original equation in the domain lie on the left of s is equal to minus 1. As we shift the s-plane from origin to minus 1, that's why there are no roots in the positive, real part or the positive of the s-axis. Okay, so here is another more example. Example number 8, a system having characteristics equation like this: s cube plus 7s square plus 14s plus 8 is equal to 0. Check whether any pole of the characteristics equation lie on the right of minus 3. That means again we have to shift the s-plane from origin to minus 3. So just put s is equal to z minus 3. In place of s, you have to put z minus 3. So the equation becomes z minus 3 whole cube plus 7 into z minus 3 whole square plus 14 z minus 3 plus 8 is equal to 0. So if you apply the formula a minus b whole cube, then again you find a simplified equation, that is z cube minus 2z square minus z plus 2 is equal to 0. So if you apply the Routh-Hurwitz criteria, then you can see there is a row 0. So there is a row 0. If there is a row 0, then you have to apply or you have to calculate the characteristics equation using the coefficient of the previous row of the row 0. So just write the auxiliary equation Az is equal to minus 2z square plus 2. So this is our auxiliary equation, and you have to find the derivative of this auxiliary equation, that is dAz by dz is equal to minus 4z. So in place of 0, you have to write the coefficient of the derivative, that is minus 4, and again go on. So this is our first column of the Routh array, and we can see there are sign changes. So there is a sign changes in the first column, so the system is unstable. Now how many sign changes are there? So here one sign changes, 1 to minus 2, here is one sign changes, and minus 4 to 2 there is one another sign changes. So there are two sign changes. That means there are two poles in the right half of minus 3. So you have to keep in mind. So that's all for today's lecture. So in our next lecture we will discuss in control action basic concept of PI, PD and PID controller. So before ending this session, just let us take a quick recap from the previous two lectures. What we understand or what we just know. That is, in our lecture 13, 14 and 15, we just discuss on characteristics equations. From the closed loop transfer function, we have to find the characteristics equation from the denominator, that is 1 plus gs hs is equal to 0. Now why it is called characteristics equation? Now from this characteristics equation, the roots of the characteristics equations are the poles of the system. Okay, poles of the system. Now depending on the poles of the system, we can find the nature of the system, whether the system is stable or unstable or marginally stable. That's why this equation is called characteristics equation. Now from this we can see that if any poles are present in the right half of S-plane, that means in red shaded zone, then the system is unstable. That's why this region is called unstable region. And if there are any poles present in the left half of S-plane, that means in green shaded zone, then the system is stable. So this area is denoted by or represented by stable region. And if there is any poles present in the imaginary axis, that is j omega axis, then the system is marginally stable. So there are three conditions: stable, unstable and marginally stable. Okay, and next we studied about Routh-Hurwitz stability criteria, how we can find the stability of a system, whether the system is stable or unstable or marginally stable. Now to find the stability of a system, you have to calculate the Routh array, and after investigating the first column of the Routh array, we concluded the stability of the system. Now if all the elements of the first column of the Routh array is of same sign, that means whether all the elements are positive, if all the elements are positive, or if all the elements are negative, then the system is stable. If there is a sign change, that means one positive to negative or negative to positive, whatever it is, then the system becomes unstable. Now when the system becomes unstable, that means there is a pole or many poles present in the right half of S-plane. Now how many poles are present in the right half of S-plane? We have to find this by seeing the number of sign changes. If there are suppose there are two sign changes, that means one from positive to negative and one for negative to positive. That means there are two sign changes. If there are two sign changes, that means there are two roots present in the positive real axis. That's why the system become unstable. And there are some special cases. If any if any if any element of the first column becomes 0, then what we have to do, we have to find that by substituting the 0 uh, by a by by epsilon, where epsilon tends to 0. That means epsilon is very close to 0 but not 0. Okay, so and next there is a rho 0 condition for marginally stable case. If there is a rho 0, then you have to find the auxiliary equation by using the coefficient of its previous row. Then again you have to differentiate that auxiliary equation, and using the coefficient of this auxiliary equation you have to find, or you have to proceed further. So, and again there is relative stability. Suppose you want to find, is there any poles present in the right half of -3 or -1, then you have to shift the j omega axis in that position, that is -3 or -1, and then apply the Routh-Hurwitz criteria and find the stability of the system. So all this we see in these 3 lectures. So that's all for this 3 lecture, and in our next lecture we will discuss on control action, some basic concept of PI, that is proportional plus integral, PD, that is proportional plus derivative, and another is PID, proportional plus integral plus derivative. So thank you so much. Thank you for watching.